Hello. In this video, we are going to again examine the kinetics of unimolecular reactions in the gas phase, where we also have the presence of an inert gas. This is part 2 of our examination. To recap from our previous video, if we have the simple unimolecular case, we have a reactant molecule A that collides with another molecule of A with a rate constant K1 to form an activated version of A, which we have as red A star here, plus leaving the other A as it was before. We have collisional deactivation of the reactive red A star with A to deactivate back to two unreactive molecules A with a rate constant K2. The activated molecule A star forms a product with a rate constant K3. There is no reverse reaction. To add the extra complication of the inert gas, we have another set of equilibria. Here, the inert non-reactive gas is a green M, so we can have A colliding with M with a rate constant K4 to activate blue A to the reactive A star and leaving the inert molecule as it was before. We can have collisional deactivation of red A star with M with a rate constant K5 to deactivate red A star back to ordinary blue A. You might notice in comparison with the previous video that I've written this particular reaction to the side here as opposed to down here, just so that we have more space available to show the succeeding derivations. Our first step is to find the rate of change of our reactive intermediate red A star. Notice that we have two reactions that form red A star. So we have the first A plus M giving us A star. And we also have a second one, A plus A, giving us A star. So we have two sources of A star. On the other hand, we have three different ways that we can decrease the concentration, the ways that we can lose some A star. So we can have collisional deactivation of A star with the inert gas M. We can have collisional deactivation of A star with A itself. And we can have the transition of A star turning into product. First, let us show the two ways that we can increase the concentration of A star. So the first is A collides with M with a rate constant K4. So this is our K4 times A times the concentration of M. The second way is that two A molecules can collide and end up forming our A star. And this happens with rate constant K1. So this gives us plus K1 times the concentration of A squared. Now we include the three possible ways that we can decrease the concentration of A star. So the first is collisional deactivation by colliding with an inert gas molecule, which happens with rate constant K5. We can have collisional deactivation just by colliding with a unactivated A, and this happens with rate constant K2. And then the final way is we have conversion of A star into our product P, which occurs with rate constant K3. At this point, we can now apply the steady state approximation, where we assume that since the concentration of A star is small, that the change in its concentration over time will also be negligibly small, so we can set it equal to 0. Doing some slight rearrangement, we get the following expression: K4 times the concentration of A times the concentration of M plus K1 times the concentration of A squared is equal to K5 times the concentration of A star times the concentration of M plus K2 times the concentration of A star times the concentration of A plus K3 times the concentration of A star. And one thing which becomes easier to see with the color coding here is that each expression on the right-hand side involves a factor of A star. So that suggests to be a good idea to factor A star out of the right-hand side. Factoring out, we get this particular expression. This also suggests that we can solve for the steady-state concentration of A star simply by dividing each side of the equation by this factor that we have here in parentheses. And this yields the following expression for the steady-state concentration of A star. So we have this particular fraction. And we're almost where we want to be because we have one final reaction that we can look at again. And we know that the rate of formation of the product is equal to the concentration of A star times the rate constant K3. So we simply need to multiply each side of this equation by the rate constant K3 to get the rate of formation of the product P. That gives our rate expression for the formation of product at the steady state as K3 times the quantity K4 times the concentration of A times the concentration of M plus K1 times the concentration of A squared divided by K5 times the concentration of M plus K2 times the concentration of A plus K3, which is admittedly a very complicated expression. What we are going to do for the remainder of this video is to take this particular expression. We are going to put it up in the left-hand corner of the board so we have more room. And we're going to look at very special cases and see, under those special cases, how it transforms the rate expression. The first special case that we will examine in this video, which we call case 2, because we went over case 1 in the previous video, is the situation where the rate constant K4 is equal to the rate constant of K5 and is equal to 0. That means that the inert gas molecule doesn't activate the reactant molecule, it doesn't deactivate it, and or the equivalent situation is that we have a concentration of M which is identically equal to 0. We have no inert gas at all. Let's see how this transforms our rate expression. Well, we noticed if K4 equals K5, then this particular expression here involving K4 becomes 0, and this expression down here involving K5 becomes 0. That leaves us with the expression that the rate is equal to K3 times K1 times the concentration of A squared divided by K2 times the concentration of A plus K3. This expression should look familiar because this is precisely the rate for a unimolecular reaction in the gas phase where there is no inert gas. So while this is kind of straightforward and expected, that is a good sign, which gives us confidence that our more complicated rate expression involving an inert gas is correct because it is true under one of the special cases. For case 3, we are going to look at the situation where the concentration of M just happens to be equal to the concentration of A. Therefore, we'll be able to replace the concentration of M by the concentration of A inside the rate expression, and we'll see what we get. At first, we get K3 times the quantity K4 times the concentration of A squared plus K1 times the concentration of A squared divided by K5 times the concentration of A plus K2 times the concentration of A plus K3. And the presence of all these A's suggests that we try to factor the concentration of A, or the concentration of A squared, out of each expression. And we get the following expression, which again bears resemblance to the unimolecular reaction in the gas phase with no inert gas. Here it appears that we replace the rate constant K1 by the rate constant K4 plus K1, and we replace the rate constant K2 by the rate constant K5 plus K2. Recall that this is only going to be true for a brief period of time when the concentration of M happens to be equal to the concentration of A, Because recall, as time proceeds, the concentration of A is going to drop because it is going to be eventually converted into product, whereas we have no mechanism in our scheme for the concentration of M to decrease or increase for that matter. For the fourth case, we want to examine a situation where the concentration of M is very much greater than the concentration of A, or equivalently, that the concentration of A is very much smaller than the concentration of the inert gas M. To do this, we first want to slightly rearrange our expression for the rate in the general case into a more suggestive form, which will make certain approximations easier to implement. Our rearrangement gives us the K3 times the concentration of A times the quantity K4 times the concentration of M plus K1 times the concentration of A, divided by, the denominator is exactly the same as before, K5 times the concentration of M plus K2 times the concentration of A plus K3. At this point, now we can implement the fact that the concentration of M is so much greater than the concentration of A, which means that in this particular sum in the numerator, K4 times the concentration of M is so much greater than K1 times the concentration of A that we can essentially neglect the K1 times the concentration of A. Similarly, in the denominator, K5 times the concentration of M is so much greater than K2 times the concentration of A that we can drop out this K2 times the concentration of A in the denominator. So let's see what that gives us. And we get the following expression, K3 times the concentration of A times K4 times the concentration of M divided by K5 times the concentration of M plus K3. And again, one can notice a lot of similarities to the expression for the rate of a unimolecular reaction in the gas phase with no inert gas. And if we compare it carefully, it looks like we replace the K1 times the concentration of A part of the numerator with K4 times the concentration of M. Therefore, the activation step involving collision with the inert gas is much more important than the collisional activation of A with another A molecule, which makes sense because if we have a situation where the concentration of M is so much greater than A is more likely to collide with an M than with another A. Similarly, in the denominator, where we would have had the K2 times the concentration of A as our deactivational step, here because M is so much more common than A, the collisional deactivation through with the rate constant K5 is very much more important than the rate constant K2 times the concentration of A. So we see that again we can rationalize why we would get this particular type of rate expression. Now that we've gotten here, let us look at one more special case within a special case, the case where the rate K5 times the concentration of M is very much greater than the rate constant K3. That means that the sum K5 times the concentration of M plus Km can be approximated as just K5 times the concentration of M, which we have put in our denominator. Now we notice that we can cancel the concentrations of M to get the following final expression for the case where the concentration of M is so much greater than A and K5 times the concentration of M is much greater than K3. That gives us an overall rate expression now of K3 times K4 times the concentration of A divided by K5. So we see under this special set of circumstances that the rate is going to be distinctly linear first order in the concentration of A. Well, let's look at the other case while we're here. Suppose instead of K5 times M being much greater than K3, let's assume that K5 times the concentration of M is much less than K3. So in that case, we can approximate the denominator simply by K3, and let's see what expression we get in that case. We get that the rate is equal to K3 times the concentration of A times K4 times the concentration of M divided by K3, and we realize that we can simply cancel K3 from the numerator and the denominator to get our final expression for the case where the rate of conversion into product, K3, is very much larger than K5 times the concentration of M. Canceling, we get that the rate is equal to K4 times the concentration of A times the concentration of M. Therefore, the rate is first order in A, first order in M, and overall, in concentration of the gases is going to be second order. We have a number of interesting cases still to look at, but because this video is getting quite long as it is, we are going to postpone them to the upcoming Part 3. I thank you very much for your attention. As always, have a good one.